This bit of notes is about significant figures. Significant figures is a phenomenon in science, and what it refers to is that the digits in a measurement that you're taking all have certain value except for one digit that is estimated. This can happen whenever we have an instrument and we can read that measurement instrument out to a number of decimal places. The last decimal place is always an estimate. So in the case of the atomic clock, this decimal place is determined by how accurate that particular clock is. The atomic clock obviously is very accurate, and so all of these digits are known, and this is an estimate. So when do we use significant figures? We use them when we're recording measurements. When we're recording the measurements, we look at the instrument itself and determine how far out I can read that particular instrument. How many decimal places can I read out that particular instrument? And then I add an estimated value. And we're going to be practicing this in class on actual pen and paper representations of instruments and on real life instruments as well. So we'll get a lot of practice with this. We're not going to talk much about this in our note taking. We'll be doing that with some activities in class. But when we're recording measurements, we include all of the known digits, the ones that we can actually read off of the instrument, plus one estimate or uncertain digit. The estimated digit becomes our last significant digit in our measurement. We also use significant figures when we're doing calculations, and that's what we're going to stress in this set of notes today. We're going to stress how we calculate how many significant figures we have when we're doing calculations. So how do I know what numbers are significant? There's a couple of rules that we follow. First, when we're looking at a measurement, the estimated or the last digit is always significant. So if I have a ruler, I can read out to the hundredths place, and so my measurement is taken to the thousandths place. All of the digits, including the one that goes out to the thousandths, they're all significant. All non-zero numbers are always significant in a calculation, and if I have a zero number, I follow the zero rules. So what are the zero rules? Well, first, leading zeros that I find at the beginning of a number, are never significant. So to give you an example, in this particular number that I've written down, it could be a measurement that I've taken, all of these leading zeros at the beginning, are not significant. So this particular number has only two significant digits, the 2 and the 7, the non-zero numbers. Remember, non-zero numbers are always significant. Captive zeros that I find between non-zero digits, are always significant. So in this particular case, this number right here, 20.00023, all 7 of these digits are significant. The non-zero and all of these captive zeros. So this particular number has 10 significant figures. And finally, trailing zeros at the end, can sometimes be significant and sometimes not. They're not significant unless there's a decimal point. So in this last rule, this particular number, 230,000, these zeros would not be significant. This particular number has only two significant figures. In this particular case where I do have a decimal, 12.00, these zeros then do become significant. So this 12.00 has 4 significant digits. This 130.0 has 4 significant digits, and this 150.00 has 5 significant figures. Okay, so let's see how many significant figures we have in each of these examples. So in this first example, how many significant figures do I have? Right, I have 6 because I have no zeros. All non-zero numbers are significant. So in this case, all 6 of these numbers are significant. What about the next case here? Captive zeros are significant, so I have 3 significant digits here. In this case, right, leading zeros are never significant, so I only have 2 significant figures here. Here, Right, because of this decimal, all of these zeros become significant, so this particular number has 4 significant digits. This one, 2 significant digits because trailing zeros are only significant if I have a decimal point. What about here? 4 significant digits. Leading zeros are never significant. Captive zeros are always significant. So this particular number has 4 significant digits. Here, these are captive, so they're significant. They'd also be significant because of this decimal. Here, remember, leading zeros are never significant, even if there's a decimal. So this captive 0 is significant, but this 0 at the end is significant because of the decimal place. And again, leading zeros are never significant, even with a decimal, but these 2 trailing zeros are significant because of the decimal. So I have 4 significant digits. And finally, this one, 3 significant digits. Trailing zeros are not significant if I don't have a decimal place. Okay. One last thing we're going to take a look at in this note group is that we're going to take a look at how to make our numbers out to the correct significant digits when we have calculations. So there's a general rule for all operations, whether it's addition, subtraction, multiplication, or division, and that is that the answer can have no more significant figures than the measurement with the least significant figures. Now, there are 2 separate rules for addition and subtraction and multiplication and division. Let's first look at multiplication and division. In multiplication and division, the number of significant figures of the calculated result is the same as the least number of significant figures in the multipliers. What? Or dividers. So let me give you an example. If I'm going to take this number, 12.31, and I'm going to multiply it to 1.5, I get on my calculator a number that comes out to 18.465. But where do I round it off to? I round it off based on significant figures. So my significant figures, in this case, this has 4 significant figures and this has 2 significant figures. So since the smaller of the 2 has 2 significant figures, I'm going to round this number off to 2 significant figures. So I would round this number off as 18 centimeters squared. Okay? This is a known value, this is uncertain. Now I know what you're thinking. If you're a math person, you're like, how can this number be more proper than this number? This is a better number mathematically, but this is a better number scientifically, because remember, scientists, when they report a value, whether it's been calculated or measured, only want to have a placed value of uncertainty. So if you follow the rules, you will get all known values and only one place value of uncertainty. Okay? So a known value, and why does this matter? Well, because a known value of x, when a known value is multiplied or divided by another known value, it gives us a number that's known without any doubt. When an estimated number is multiplied or divided by another number, it gives us some doubt. And scientists only want to work with numbers that have one place of doubt or one estimated number. So let me show you how this works. So here we have 2 numbers, just like in our previous example. I have 4 significant figures multiplied by 2 significant figures. So these 2 numbers here are estimated values. The rest of the numbers here and here are known values. Watch what happens when I multiply these 2 numbers together. I have an estimated times an estimated, that gives me an estimated number. An estimated times a known gives me an estimated number. An estimated times a known is estimated number. An estimated times a known is an estimated number. Now, if I'm going to continue with my multiplication, it may have been a while since you've done this without a calculator. We have known times an estimated, which is an estimated. Known times a known, which is known. Known times a known, which is known. Known times a known, which is known. Now let's add them up. This becomes an estimated number. This, of course, is an estimated number. This is an estimated number. This plus this becomes an estimated number. And this is a known. So notice, if I round this off using the rules that you were given, 4 significant figures, 2 significant figures, I should round this to 2 significant figures. Okay, so when I round it to 2 significant figures, I only get one estimated number in my answer, and that's what's important to scientists. It may not be as nice of a number mathematically, but it's a better number scientifically. One known and one estimate. You don't have to figure this out every time. If you just follow the rules of a multiplication and division and addition and subtraction, you will end up with an answer that has only one estimated value. Okay, let's take a look now at the rule for addition and subtraction, because it's a little bit different than the rule for multiplication and division. So in addition and subtraction, the resulting answer must be reported to the same number of decimal places as the term with the least number of decimal places to get one unknown value in our significant figure. So here's an example: 12.075 added to 3.4, and I get an answer of 15.745. But notice, since 3.4 only goes out to the tenths place, then I would round to the tenths place. In doing so, that works out so that this last number, this 5, is my only estimated number. The rest of these are known numbers. And we could work you through the same process that we did with the multiplication, but trust me, if you just follow the rule, you don't have to work it out like that with estimated knowns. You simply follow the rule and you end up with the right number of significant figures, because only my last number is an estimated value. Okay, we're going to be doing some practice in class, so get ready.